be our
The
strategy.
foreign servers have the same length of data, means they'll say it differs from data, I mean, from the number of times.
So the
That means we can say 64 MB is the max limit for that. So
oh, that's a fixed size.
Yeah, fixed size. Overall, for 64 MB will be for each and everything. Sometimes it will be only 62 MB, 62 MB.
62. So yes, that's a good question. So what about for files less than that? They will use a padding. So still, 64 size will be kind of the padding part. So where the replication will happen, that's a strategy that can change. But typically they have also within the rack, across the rack.
For particular data, when we are checking, and how does it map? Like, is it using some kind of mapping, or else it's checking for everything? Because checking everything will take time. And
so the checking, I mean the what's the access operation for file system? File open, file closing, and then two main reading and writing.
But the thing is, for each server there is a different address. So
chunk server has a different IP address. Yes.
Yeah. So for particular IP address, we can able to check which is one is there. But where we don't know where is the particular location in the chunk server we want. So actual chunk server is
chunk server and the offset is a part of the API.
So we can directly.
If you rather than chunks, start from a file. So here's a big file that has maybe two chunks.
But the searching takes a lot of more than time.
What's that?
Searching the data in the chunk server takes a lot of time, right?
Let us go through how the reading and writing is done. Okay. So here is the big file that has two chunks. Okay. The reading this is what we said briefly, but we want to go over again because that's important, right? So I have a picture later. So clients will send a message, I want to read this file. And chunk index this file's chunk, third chunk or second chunk, okay? Master says is that here's the chunk ID 64 and chunk the version number in case the file is updated, and location of replicas, that's a chunk server's addresses. Among those, here's a very important word, closest one. Who chooses? Client. Client chooses that, I out of these three replica meaning chunk servers, so two chunks. First, chunk 1, 3 copy. Chunk 2, 3 copy, right? So I need to read this chunk 2 and 3 copy. So I can access any three chunk servers. Out of those, client, choose the closest one based on the IP address. The difference between my current client's IP address and the chunk server's address, if it's the smallest one, they consider it as the closest one. Okay? So previously in the same rack or nearby rack, the same subnet, right? That's for reading. For writing, did anyone remember the keywords about the writing? Here I already said primary. What other keywords? Tell me what's the keywords over here. Hint. It's in blue. It's in bold. What's the keyword? What's the keyword here?
It is taking leads to write.
Just say the keywords. Just tell me the keywords.
Heartbeat messages.
The hint, first of all.
Primary.
Primary, basic.
Primary.
Yes.
Heartbeat messages. And
Daisy chain.
Daisy chain.
Sorry, primary and daisy chain.
So there are three keywords in bold, right?
Pipeline, primary, daisy chain.
Right. Primary is necessary for writing. You don't need it for reading. Reading chunk server, 2 chunks, the 3 copies, 2 copies. The chunk 2, I just need to choose closest one of them. That's enough. Other clients can use another chunk server for the same chunk. Parallel reading, performance, reliability as well as performance. For writing, we need a primary. Writing has to be done. It also means that 3 times. The writing has to be done on 3 chunk servers for 1 chunk, right? For taking care of that 3 copies, that's what primary will do, and it is done in a daisy chain manner. How does daisy chain look like? It looks like this, and then what? Not like this going down, chain. That's a daisy go down. Okay, that's a daisy chain, right? Pipelining is that you start something before you finish the earlier one. It's a little bit different from parallel. Parallel meaning is that you can do it start at the same time. Pipeline is that you have to start this one first, and before you completely finish, you start next one. Before you completely finish, you start next one. That's pipelining, right? So here's the write operation. I thought there was a picture. So the earlier picture, actually, it shows the write operation. This is write operation. This is a read operation, right? Writing. Client, hey, I need to write this file. Okay, you can write the file on this, chunk servers. Here's a primary. It knows a primary, so 3 and 4 actually happens almost at the same time. For talking to primary, I'm writing this file. I know you are the primary. Please take care of it. Meaning that getting the acknowledgement. Look at the thick one, thick arrow, number 3. What's the thick arrow about? Data, not control. So file is written. Client, how many times does it write a file? Chunk? How many times? How many arrows are coming out of the client?
1.
How many big arrows are coming out of it?
1.
Just 1, right? What about the other 2 copies? It's done among the replicas. So this replica, I got this chunk that I have just written. Actually, before it's finished, you can do that. It sends it to the next replica, next chunk server, and then this one sends it to the next. Okay, so they take care of these replications. Client doesn't have to have a big 3 arrows, big arrows, right? Just 1 enough. And then this primary, whenever they are done, they will be in communication with the primary when all the writing is done. It tells primary writing is done. Okay. So client know that, okay, my writing operation is finished. So this is what is a daisy chain? Sorry, your name? Uday. Okay, so here's a daisy chain. This is daisy chain. So this is a daisy chain. And then what about pipelining? Pipelining happens over here and here, where is replica A. While it's receiving the chunk, it can send it out to the next. before it finished, it can send it out. Where is it receiving it from? Or to? Through Ethernet. Ethernet bidirectional link. It can receive and transmit at the same time, right? So pipelining means that in and out can happen at the same time. Of course, not at the exactly beginning. He started to receive this much, and then before I get another one, I started to send it. You know, that's a pipelining. So did it make sense? Okay. If you don't have a big picture, you know, you just put the name of the servers and have a random operation. It's important for you to know exactly how it happens and why it happens. That way you understand and appreciate the technology, right? So GFS, the meta information, in other words, namespace. It's atomic, meaning that it's done by it's done or not be interleaved by something else, right? The atomic operation, it's not atomic bomb, right? It's a single operation. Because done by a single master, that's how they decided to use it. I want you to question all these things because it's published in 2003. They have done this in 2002, that means. And then a lot of time has passed since then. And of course there are changes, and you would wonder what are the changes it has made since then. So I want you to first of all understand how they work, and then question. You know, does it still make sense this time? I'm almost giving you a hint by saying that at this point, right? Right. They also have some different data update semantics called consistent and defined. Defined is actually the thing you would think after data mutation, meaning data update. Their data update is called mutation. It's Google File System terminology mutation. Then all clients will see the entire change. That's what you would think in general. However, that's not the thing to do. They have a special case. It's quite possible. But there are other cases that it's more lenient in a way that clients see these changes, but then when you see the changes, where the changes are could be different. They have an error detection mechanism, and then master. You should question, what about it dies if it's a single, then tolerance mechanism is that having a backup, it's a memory, and something has to be stored, and it is in logging. You do see actually logging-based file system occasionally, and the Google File System does that. Chunk list and version number is to take care of the writing. I'm going a little fast, but I'm still going to, I will ask you in the sense I want you to understand it well, right? So the point of logging is that it can replay the log. You know, this file was created, this file was deleted, this file was added. You know, all these logs will be replayed to recover from it. But where is the log? Log itself is in the disk, not in memory. Right? But master, once it reboots, it has to replay and get up to the previous state. It was a huge success that supported Google's lots of diverse services and applications. High availability, recoverability on a cheap commodity hardware was a big success. If you see this the idea high throughput by decoupling, controlling data. You see, what's the keyword here? Hint. It's not by, it's not and. High throughput by decoupling, controlling data. So the keyword actually, except the by and end is everything. But if I were to choose first, is a decoupling. You know, you see a lot of idea that comes out of decoupling or coupling. Okay, so you see a lot of idea that comes out of doing it in a distributed manner or doing it in a centralized manner. Right? The Google file system, the master is really centralized, a single, right? But here the real idea is that control and data information separation. Okay, so the so the control information handled by the master server. Data is handled by chunk servers. You see, if you look at a lot of things we do in everyday life or even history, you see decoupling. You know, when I think about even hospital, nurse, the doctors, it's a decoupling practice. In older times, there was no nurse, and the doctors used to travel to the patient place, doing all the things, and his capacity, because of all the other things, he couldn't save a lot of people. Decoupling some of the tasks and to give it to, say, admin, and nurses. The doctors can focus on maybe diagnosis or surgeries, the main part of this task. That's a decoupling. Here it is decoupling of control information and data information, right? By doing so, high throughput was achieved. Yeah, so what kind of the semantics, if you recall the Unix session, immutable transaction, those sections are not exactly known to applications, and those application has to figure out what they need. This is not silver bullet that hits all. It's only for some of the applications for Google, not for maybe your application, or not for every application in Google either. One of the main things that the workload, write once, streaming read. Don't read back and forth. It's not like the sorting, things like that. Right? Okay. Questions? So GFS, when was it published again? 2003. So more than 20 years. Wow, right? So you can imagine that it has changed. They have been making changes incrementally, so they didn't make a publication. But over time, they made the changes, and then they made the main the terminology changes as well. So the later version is called Colossus, means gigantic. And it can be also called GFS V2. So what do you think? We saw now how GFS was designed, works, right? What are the areas that might needed changing, considering maybe bigger scale, 1,000 to, the number of servers, the several thousand to 2-3 magnitude order higher. Data size, terabyte, now hundreds, thousands of petabytes, right? So everything is a lot greater in scale. So what do you think? What's the part that needs to be, that probably changed? Just throw any part of it.
Reduce latency.
What's that?
Latency.
Latency between what? All the processing. So they have to. The point is that they have to handle bigger number of data, greater amount of data, right? The number of files, and then total amount of data is all bigger. Number of access is bigger as well. So they have to perform, fast enough. So doing fast, of course, that's the first priority, right? Maybe replication factor increasing to 5. I don't think that probably you don't think it's not the case. That's not an issue, okay? So how can they make it faster? Or what could be some problem, potential problem of GFS that you have seen so far?
Increasing chunk server file size.
Increasing what?
Chunk server file size.
Increasing number of chunk servers? Yeah, then it's not called the file system change or upgrade, right? That's definitely happening. Number of servers, chunk servers, it's number of files. Yeah, they said it's a multi-magnitude higher, greater now they have to deal with. So what I'm asking is that what kind of architecture change, or you don't have to suggest that it has to be changing this way, but what could be the part that you think that it's not, may not be good enough to handle larger scale? This is not a difficult question. I think even somebody, when I presented, somebody could say that. So let me narrow down. Between master server and chunk server, what could be more, where could be a more bottleneck? Master server.
Maybe because it's centralized and
Exactly.
the chunk server has distributed.
Right, that's what. Single master server. It's, why do they do it single? Not because it's faster, it's because it's simpler. And doing it fast is addressed by putting in a main memory, not on the disk, right? But still, being done by one CPU, it may not be scalable. That's the major part, right? Probably other people, I think, you were thinking, right? Just didn't say that. So, master server, the one machine, not enough. It was fault tolerant, but not really high availability. If fault happens, then there is a log, but it has to be always up. And the performance was not fast enough, depending on the number of requests. So the GFS, it's not a lot different. First of all, the version 2 classes. In the exam, I might ask you just a few minor things, these names, but I really want you to feel and appreciate the design. Bigger scale, better performance, even for the kill latency. Extreme cases, we don't want it to be poor, right? So that's what they wanted to do, and the change is this. Just in terms of name, master is called now Colossus, and chunk server is called just D for data. Okay. And then they had the really file system on top of a storage that supports a lot of application, but they put most of things on a database actually, database which does store data, that they does offer many important operations, and then also fast. They have their own semi structured database called big table, and that's what actually they put this information. So the the let me actually, so the big table has all the major key information, and also the classes master, the key value store, meaning that meta and the chunk server information. They I mean, for now I don't want you to be intimidated by a lot of these different ecosystem names. For now, just remember they do use GFS, but this meta information is stored on a database called big table. Okay, so big table is again the semi-structured, meaning the data can be put in a table, relational table, the database. So this is the database where it can have all this mapping between file name and chunk server, this meta information, and it can does the query quickly. And it's all these searches done at the hash index level. It's not doing a search one by one. I think that's another question they asked. So here's the main change. Chunk server is called whole classes, and that information is in a database. Database with the earlier one, it shows that master server is not just one, it's multiple. And then the question is, what about consistency? Didn't they wanted to make the consistency simple, so that's why they decided to have one? Well, I'm telling you, one is not enough for performance. They have to have many. Then what about the consistency? There has been traditional algorithm called Paxos, and they implemented it and make it work good enough for their server consistency. Paxos. Actually, the name Paxos you will see later in software-defined network in the later part. So for those who, I taught Paxos in just the blockchain class, and if you are taking distributed operating system, you might also hear about it. So that there's an algorithm to ensure the consistency of the multiple nodes, multiple distributed nodes. Okay. So they do have a mechanism to offer some level of consistency among the master servers. Okay, so that's what it is. So it's not exactly all gone just renaming and putting this data on big table. That's the thing. You see that chunk itself, chunk replication, it's all similar. The way reading and writing is done, it's all similar. Okay. So I think that's it. So a little more detail. The curators are basically the part of the classes that has the metadata service. D is the chunk server. They are connected over the network, and then underneath they do use RAID. So the file system also handles RAID. Is for the RAID to work, you have a hardware or software level RAID driver, and it does all the computation at the lower level. File system works with it for error checking, reliability, and so on. So I will let you guys to take a look for those who are interested, and I want you to read it, but let me move on to the next one. So that so today we want to also do MapReduce in Spark, and next week we want to talk about the network virtualization. So let's say guys something. You can take a look. And that's how you do interface architecture for the front end with the front end and back end. That's about the rest we can. So next we want to talk about now Hadoop and Spark. So raw data on a storage, and you have a file system that allows the arrangement, metadata management, and the read-write access, right? That's a Google file system. But still, that's not enough for developer to do programming that exploits the parallel resources, right? So the platform that allows that is called MapReduce, and then it has some content. It has the disadvantages, and then Spark appears. So I told you Google File System. Why do we just talk about Google File System? What about Amazon File System? The Google File System inspired the Hadoop File System and inspired the all other cloud, level distributed file system. So the Hadoop is the name for distributed file system that mimics Google File System. So that's a Hadoop, or file system is underneath, right? On top of that, there will be a so-called programming platform that allows the parallelism for the developer. It started from Google, MapReduce, then it became the Apache, the open source project. So if you look at the public cloud, AWS, Azure, when they say EMR, what does EMR stand for? EC2 is Elastic Compute Cloud. EMR means Elastic. MR, what do you think? You have this word, MapReduce. So EMR, so if you know these things, when you see the services available from public cloud, this is about the MapReduce. We are not going to talk about the detail much, but at least another one. There is a Mesos. So you might ask, here's a file system, typically an operating system. So whenever you think about the cloud level or distributed operating system, you want to think about what the similar thing, how similar things are done in a local system. In operating system, Windows, iOS, what do they have? What do they have is that important thing is that the CPU scheduler, which job gets done first, the limited resource who does scheduling, the high priority job or the first job first, those resource scheduler is one of the main key brain of an operating system. Probably cloud means that too. So, before anything was formally introduced as a, first come first served, was fine, but the paper called Mesos was published that allows the load balancing of the servers that does the load balancing. This server is less busy. I want to allocate this group of servers to the new users, things like that. So that kind of scheduling, the platform was proposed, implemented, and then later it became an open source project, and community they contributed further, and it became really international scale open source project, which is all adopted by other cloud providers. Bigtable is the one that will influence the hype. Okay. So told you GFS, we talked about it, at least entire class, or 2 classes. Now Hadoop file system, I'm going to talk about it in 1 or 2 slides. Here it is. So the type of the data, characteristics of data that the cloud provider they had is like web log, crawlers, data, healthcare data, pension information. These are the ones that are written once, and streaming read, that's a read once for one client, but it can be read by many other clients, right? So this is this type of data is also called worm. And because of this type of data, this programming model, MapReduce, was inspired. So what is MapReduce? It's a parallel programming model or platform. So Hadoop file system, this is a file system, right? It's basically the same as Google file system. I'm showing just one picture. You see there's a name called name node, and then there's a node called data node. Okay? And the name node does the metadata interactions. Data node is the one that enables reading for clients or writing for clients. So it's basically all the same, right? Except the different name. What was the name for name node in Google file system? Master, right? What about the data node? What's it? Chunk server. Yeah, that is it. So no worker, right? It's in this case. I know, but why did the name and the worker node actually is there in MapReduce? So it's basically the same. And that's it. Okay. Now back question. Okay. So now MapReduce. I was serving on a National Science Foundation panel. I'm not supposed to tell what kind of proposals that I have seen reviews and things like that. But a little hint that program is really handles about the support of this kind of project. The next level of Spark. Okay, for example, yeah. So you see, they recognize those names that the people, and they are also in the panel as well. So the MapReduce, what is it? It's a parallel programming model or platform. Okay? So the parallel programming, it's a field that has been there for a long time, and maybe you were too young to think about it, but before MapReduce, we had a parallel programming. Right? You can do that. We have the Linux fork thread and you do process synchronization. It's a lot of work for a developer, programmer, and things can go wrong. It's hard to debug, right? So it's not that it's impossible, but doing it all one by one, case by case, handled by a developer, programmer, it's a lot of headache, right? So MapReduce just make things all handled by this platform. So developer, programmer doesn't have to do much about the much of the work. That's the thing. Just like Google file system, if GFS doesn't do 3-factor replication, user has to do another copy, and all those things. It's not impossible that having a copy of files, but it's just a lot of work. Now with the GFS, it's all handled at the file system level, right? It's just I really want you to understand what does this platform means. So TCP, HTTP, all of the web. You saw that, let's see whether your admission on UMKC, it says, oh, congratulations, you're admitted. Or it can be some completely different word and that was a mistake saying that you are admitted. That never happens, right? What you see on the web is correct one. We call it reliable data transfer. It offers, the data that was what was original. In reality, underneath network, some packet may be dropped and it could be retransmitted and all those things could go wrong. However, at the TCP level that HTTP uses, TCP level handles all of the reliability. So user doesn't have to care about, oh, is this the no means yes, or you don't have to think about all these redundancies or missing information, things like that. Isn't it cool? Reliability is done at the lower layer, at the TCP layer. That's what they handle. So it's not that it's impossible to eventually have the reliability done at the application layer using UDP, just that underneath lower layer it takes care of it. That's exactly the case like MapReduce. Parallelism handled by this programming platform, so that developer can be doesn't have to have a lot of headache. So motivation is that parallelism is so important. Single machine cannot do it. We need to do it. We need to use a lot of machines, but something can fail. So can a platform handle parallelism, distribution, fault tolerance, all automatically? Okay. That's the idea of Hadoop MapReduce. The idea is that we use this word many times. Let's do scale out. Let's use many small rather than one big one, right? So here, what do you see? It's a parallel programming platform or model, but it also does what does that mean? The data is distributed to different nodes, and some data may fail, and still those things are all handled by this platform. Okay. So that sounds really cool. In order for, if you have this idea of how to build this system, right? Think about the workload of how the programmers are going to, so what you have to offer is the APIs. This MapReduce offers APIs, basically map and reduce, and with that you take care of parallel programming. So they characterize the applications, and this is the API and things like first of all, read lots of data, and then map data to different nodes. You can and do the processing. Processing can be shuffling, sorting, finding maximum, things like that. Done at the small set of the data. Next stage, you do reduce. Reduce could be aggregation, summarization, filtering, transformation, like what's the sum of the data, or what's the maximum number of the occurrence, or number of occurrence of this word. Like word count is the example that I'm going to show. Given a big file, how many, which words are appearing how many times? Word count. This is application. And say data is big, you don't want to do it, you want to be able to exploit a lot of machines. So we do the word count computation on a piece of the data, and then later aggregate it. That's the paragraph. That's the support that this platform can offer. So look at this workflow. See, I'm starting from far left. Input data, split it into multiple. Now we have the word worker node. Okay. Okay, so don't get confused with the name node, data node, master, and chunker. If you understand the story, I don't think it will be too confusing. Master, chunk server, both of them are servers, and they are Google file system. And then Hadoop file system, name node, it's a namespace handling, and data node, it holds the data. It's not about the processing data, it's just holding the data. Name node, data node, okay? So those are the names. And then now we have worker node. These nodes are working, meaning processing data. So the data is split into multiple. Piece of the data are given to worker node, and they will spit out the results. The results will be aggregated, reduced, and then finally put it in output. So you see the workflow from where to where? Left to? Left to? Right, not up or back, right? Left to right, and that's it. Sequential workflow. Two main APIs or stages, mapping and reducing it. Mapping is a data split into multiple and do something on a piece of the data. That's a mapping. Reducing is reducing the data. It could be aggregating, summarizing, filtering, or transformation. Without mappers so the APIs are mappers and reducers. I really hope you would appreciate this one, right? And some people, oh, I know this is a system called API called mapper and reduce, and that's it. Underneath, you see this is amazing work that's been done. Can you do the same work without mapper and reducers? Of course, you could have done it. People have used to it. I used to do pair programming with the multi-threading. It's it takes a lot of time to do debugging. But with this support, you don't have to do that. Multi-threaded code processing synchronization, no needed. Then the question is that okay, that's it's underneath they have this the language and data processing support that does all these things. What about the some of the worker node dies? Then restarting will happen. If worker node, remember fault tolerance, auto recovery was a part of the goal, right? So fault tolerance, automatic, the balancing fault tolerance is also part of the goal. So if some worker dies, if it could actually, programmer might have to restart the program or rerun the program. But map reducer takes care of it. So that it's underneath that's all supported. Okay. So look at this. Here's the input file. Big multiple input files. Well, not so big, but I suppose it's big, and still it's split into smaller pieces, mapping, and then it does the individual computation. Word count. In this piece of data chunk, the word apple appeared once, word orange appeared once, mango appeared once, and so on. And then it's aggregated, reduce. Apple 4 times, grape once. This is the final output. So, here how many times, which one, the key value pair, this is important in a database word, key value pair, it has to be constantly updated. And reducer actually will aggregate all those things. So here's a master node again, but there's a master and worker node. So don't get confused with the name node, data node, worker node, all these things. In map reduce, there should be some process control part of the program that says that, oh, I need this many processes, right? So that's the master node. So in Hadoop program, basically it will fork meaning creating a process, as operating system word, right? That will act as a master, and it also forks meaning creating a process. This is not a data node, okay? This is not about storage server. This is just a process node, right? Compute node, which could be on the same machine. Actually, in older times, earlier, before we had a public cloud much available, in 2012 or something, the assignment used to be on your laptop. You do install the Hadoop map reduce and do this programming. So input data into split and then reduced. A lot of data is sent through the big network over there. Just the same thing. This master node will work with Hadoop file system name node to get the file, right? So don't get confused with this master and name node. You are not confused, right? Right? This is a really amazing thing, right? So failure handling is done within the MapReduce platform level. Programmer doesn't have to check if the node is alive and so on, right? So it's all done. This is an amazing anecdote. Google has lost 1,600 to 1,800 machines at once. A lot of machines were dead while working on this big MapReduce project. But it finished. Of course, it took longer time, but it finished. You don't have to do the restarting of the program. Failure handling was done. Of course, this is all great work, but hearing just one anecdote just clears all the doubt. Later, you will see Google software-defined network. They applied on WAN environment. Oh, I'm sorry about that. I'm gonna finish it. And then people were at that time just applying in the small scale university level, but Google suddenly announced that we have applied software-defined networking in the over wider network, and our utilization went up almost 100%, and everybody appalled and started to believe it. This is something similar. Okay. So this is the end. Mapper and reducer. In the program, you just override the class system. You extend the class and you put it in the code. It's that simple. Okay, I want you to actually try it yourself. And that's it. So next time I'm gonna briefly talk about Spark. Probably, how many of you have heard of Spark? Yeah, well, the majority of you, right? So Spark has been really sparkling ever since. When MapReduce was introduced, everybody was saying, "Wow, MapReduce is amazing." Researchers, we always look for problems, right? So, well, these are the issues, and then Spark came out, and then just like the previous the anecdote, they also have an amazing, attractive story that tells the power of Spark. I'm telling you, it has been also a while, and then you can also think about any issues in the current context, like AI, things like that. You might notice some of the names, all the UC Berkeley folks. The person who was a student back then became a professor at Stanford, and then I think just moving back to Berkeley. Anyway, these names you see often in big data ecosystem. Okay, so let me stop here for today. No quiz for now, but expect a quiz next time. And so Spark will be pretty much it before we go into the networking virtualization. Okay. And then assignment 6 will be out really, right? It's not difficult, but still it will be fun.